Okay, now let's continue the lecture. Here is the 1.3 classification of differential equations. The main purposes of this book are to discuss some of the properties of solutions of differential equations and to present some of the methods that have proved effectively in finding solutions, or in some cases in approximating them. To provide a framework for our presentation, we describe here several useful ways of classifying differential equations. Mastery of this vocabulary is essential to selecting appropriate solution methods and to describing properties of solutions of differential equations that you encounter later in this book and in the real world. Ordinary and partial differential equations. One important classification is based on whether the unknown function depends on a single independent variable or on several independent variables. In the first case, only ordinary derivatives appear in the differential equation, and it is said to be an ordinary differential equation. In the second case, the derivatives are partial derivatives, and the equation is called a partial differential equation. All the different differential equations discussed in the preceding two sections are ordinary differential equations. Another example of an ordinary differential equation is, let me write down, is L, oh, it's too big, is L d q of t and dt square plus r dq of t over dt plus 1 over c q of t equal to E of t. This is equation 1. For the charge Q of t on a capacitor in a circuit with capacitance C, resistance R, and inductance L. This equation is derived in section 3.7. Typical examples of partial differential equations are the heat conduction equation. This alpha square partial derivative of this is u x and t with respect to x partial derivative of u respect to t. And the wave equation alpha square partial derivative x u x t over partial derivative respect to x and partial derivative u x and t over respect to t. Here alpha square and a square. Okay, this is a square. This term should be a square. Are certain physical constants. Note that in both equations 2 and 3, the dependent variable u depends on two independent variables, x and t. Here is x, here is t, x and t. The heat conduction equation describes the conduction of heat in a solid body, and the wave equation arises in a variety of problems involving wave motion in solids or fluids. Systems of differential equations. Another classification of differential equations depends on the number of unknown functions that are involved. If there is a single function to be determined, then one differential equation is sufficient. However, if there are two or more unknown functions, then a system of differential equations is required. For example, the Lotka, Waterer, or predator-prey equations are important in ecological modeling. They have the form dx over dt is equal to a times x minus alpha x y and dy over dt is equal to minus c times y plus gamma x y, where x of t and y of t are the respective populations of the prey and predator species. The positive constants a alpha c and gamma are based on empirical observations and depend on the particular species being studied. Systems of equations are discussed in chapters 7 and 9. In particular, the Lotka-Waterer equations are examined in section 9.5. In some areas of application, it is not unusual to encounter very large systems containing hundreds or even many thousands of differential equations. Order. The order of a differential equation is the order of the highest derivative that appears in the equation. The equations in the preceding sections are all first-order equations, whereas equation 1 is a second-order equation. Equations 2 and 3 are also second-order partial differential equations. This equation 1 is a second-order equation because the derivative is the second-order derivative. So it's a second-order and equation 2 and 3 are also second-order partial differential equations. More generally, the equation is an ordinary differential equation of the nth order. Let's write down. This big F of t and u of t and u prime of t u nth order of t is an ordinary differential equation of the nth order, is a nth order equation 5 expresses a relation between the independent variable t and the values of the function u and its first n derivatives u prime, u double prime, and so on until to u nth order. It is convenient and customary in differential equations to write y for ut with y prime, y double prime, and until to y nth order, standing for u prime t, u double prime t until to u nth order of t. Thus, equation 5 is written as f of t y y prime y nth order equal to 0. Equation 6. For example, this is, for example, y triple prime plus 2e power of t y double prime plus y times y prime equal to t power 4 7 is a third order differential equation for y equal to u of t. Occasionally, other letters will be used instead of t and y for the independent and dependent variables. The meaning should be clear from the context. We assume that it is always possible to solve a given ordinary differential equation. So ordinary means only one independent variable for the highest derivative, obtaining this y nth order is t y y prime y double prime y n minus 1 order. We assume that it is always possible to solve a given ordinary differential equation for the highest derivative, obtaining this form. This is mainly to avoid the ambiguity that may arise because a single equation of the form 6 may correspond to several equations of the form 8. For example, the equation y prime squared plus ty prime plus 4y equal to 0. This equation 9 leads to the two equations y prime or y prime. We can consider this y prime we can, if it's yt, let's use if it's z square plus tz plus 4y. Let's consider this equation, and we can solve this for this value by the formula. Z should be minus t plus or minus t squared minus 4 times 1 and 4y, this, and over 2 minus 1. This is the formula for this second order equation. And maybe, yeah, this is the formula, and we can plug this y prime into z position. So then we can get y prime is equal to minus t plus or minus this t square minus 16y and 2, and this can lead to the equation 10, which is y prime equal to minus t plus t square minus 16y square root and 2, or y prime equal to minus t minus this square root t square minus 16y 2, and this is the equation 10.